Welcome back. This is lecture 28 in our course, and today we have two objectives mainly, right? The first one is, now that we know about these 1pi sums and the complete propagators, we want to go back to the scattering discussion, especially the S matrix and the Lsc formalism, and take a second look at that. That will allow us to see what role these 1pi functions and the complete propagators play in the Lsc formalism, right? And have a first look at how these scatterings will be modified once higher order corrections are included in the theory, right? The second objective is actually another milestone for our course, because we will now be able to gather a bunch of Feynman rules we already derived, right, together with one new interaction, which is very similar to the previous ones, and put together quantum electrodynamics, which is a very realistic field theory, and also quite possibly one of the best, if not the most successful scientific theories ever proposed by mankind, right? It's one of the theories that we have tested with greater precision so far. Right, so let's start with the S matrix discussion. In order to do that, let's recall a few things that we have already discussed in the course, right? And if you don't remember these things, take a look at videos 10 to 12, and if you look at the lecture notes, this is about page 80, 85, right? And you can remember that we defined this S matrix as a transition between these asymptotically free states in the past and in the future, right? We proposed an idea where you start with states of the free theory and evolve them into states of the interacting theory, rotate them into the final states, right, by this matrix, right, and then propagate them to, again, free states in the future. Right? So that's what the S matrix does, right? And we were able to project these states of the full theory, in here the vacuum and in here any state of the full theory, into states of the free theory, right? These guys, we never wrote them exactly like that, but we wrote them as creation and annihilation operators acting on the vacuum, which is the same, right? So in case of the vacuum, we found the proportionality constant between the vacuum of the full theory and the vacuum of the free theory. In this case, we didn't. And the reason is that finding this proportionality constant that is also here, right? Once you write these guys in this way, you can also write the S matrix in this way, right? Now I'm writing the S matrix in terms of this transition between states of the free theory, right? In order to find this proportionality constant, you need to prove the Lsc theorem, right? Which we're not doing yet. What I can say right now is that you have to assume that these initial states of the interacting theory and final states of the interacting theory are somehow narrow enough. And again, defining what narrow enough means is part of proving the Lsc formalism, right? And then you can find this proportionality constant. Right? Once you do that, what you get is the Lsc reduction formula, right? So this is sort of underlying every scattering calculations that we did so far, right? This version of the Lsc reduction formula that I wrote here is a practical one, right? I removed a lot of the noise here, but this is what you get in the end. That's the part you use. Right? So you can see that on the left side, I only have the part of the S matrix that actually deals with scattering, so the T matrix, right? And on the right side, I only have the connected diagrams. And that eliminates the normalization, because remember, if you look at Feynman's theorem, you would have something like that divided by a transition without the interaction in the middle, and we know what that does. It eliminates the vacuum bubbles. Also, we have seen already that diagrams that are not fully connected won't contribute to a scattering with these many final states. So if I have these connected diagrams in the middle, they just don't have enough poles to contribute to the Lsc reduction formula for a given number of external legs, right? So that's the connected part here, right? This is a practical Lsc reduction formula because I'm only including here connected diagrams. I'm already forgetting bubbles, I'm already forgetting disconnected diagrams. The part that may not be clear, completely clear yet, is this imputated part, right? What does that exactly mean, right? So, and also I have a square root of z here. There was a leftover from cancellations of propagators with inverse propagators, which might not be fully clear yet. So the main objective of our discussion today is to understand the square root of z here and also this imputated, and the two are related, of course. Let's go through a few examples to clarify that, right? So again, we'll stay into lambda 5-4 theory, right, which is our favorite, right, and think of a 2-to-2 scattering. And we start, of course, with the lowest order possible, which is the free theory. So just lambda to 0. This formula, in this case, just tells me on the right side here that this is what should appear there. B. So I'm calling A and B the initial momenta, and 1 and 2 the final momenta. And I know that I can write those states in this way, right? There's just a big normalization to EA, to EB, to E1, to E2, times a few creation and annihilation operators. Which now I can make a few commutations and get the diagrams, right? If you're curious about the calculations, take a look at my lecture notes, but I assume everyone can now just think in terms of diagrams. So let's write diagrammatically what will come out of those commutations that I have to do there. Will be just these two diagrams, A, B, 1, 2, and the second diagram is something like that, right? This goes behind and gets there. There's no crossing there, which do not contribute because these are disconnected diagrams, right? They contribute to if I write the S matrix as 1 plus IT, these two guys actually contribute to the 1, not to the IT. Right? So let's go to the next order. Now if I go to a 2-to-2 scattering and take first order in the perturbation theory, now the right hand side of that equation, right? Again, this is free theory states. Will become this. Now I have one insertion of the interaction here, which is the time order product of operators that I'm writing here, right? I have an integral for the position of the vertex, which I'll call x, 5i to the 4x, and I have to use Wick's theorem to contract these with, I can write these guys in terms of external operators, or I can think of contractions with the external legs, right? Anyway, I mean, in every way possible, right? I have to use Wick's theorem to contract these in every way possible. Again, I have the details of the calculation in my lecture notes, but let's write the diagrams, right? a bunch of types of diagrams, right? So if I contract a few fields in here between themselves and then use the rest for the external legs, I'll get diagrams that are, let me put my, I can have a bunch of possibilities here. I'll just showcase some, right? So I have these diagrams of this sort. In this case, I think I'll write them all. I have these, and this line goes behind. There's no connecting point here. I have this. And I have this one. Oops. And these are 4 possibilities that can show up now. There's also the possibility of having a bubble diagram times the order lambda 0 correction. So these 2 diagrams just multiplied by the vacuum bubble. And finally, there's also the option when I contract 2 fields there, 2 fields there, and get this with an actual vertex here. Right? Now we know these are all disconnected. This is multiplication by a vacuum bubble of, again, disconnected diagrams. So none of these contribute, but this guy does, right? Finally, we found that first order, something that actually contributes to the scattering, right? So what I'm finding here is that IT, which can be written as 2 pi to the 4th conservation of all momenta, PA plus PB minus P1 minus P2. I'm oriented all momenta to the right here, right? I am, right? And this tells me that M is minus lambda, because this guy, right here, if I use the fine rules I know for lambda phi 4, this guy is just minus I lambda 2 pi to the 4th delta for PA plus PB minus P1 minus P2. So I just have to compare this with this, right? And I get M. It's just minus lambda, which I can use for a cross-section calculation, right? We have shown that a 2-to-2 body calculation like that, with this M will be just lambda square over 64 pi square center of mass energy, right? So this is what we have done previously, right? And I could also integrate in omega, use a symmetry factor to get the total cross-section, which is this one. And so far, nothing really is being clarified about the imputator or the Z, right? In fact, I'm using Z equal 1 this far, just because that is true for 3-level diagram, right? So I don't have to worry about the Z yet. Now let's look what happens if I go to the next order, which is really what we want to see, right? Now I'm going to lambda square order in the perturbation theory the amplitudes, right? Remember, the order I'm talking about is in the amplitude, then you have to square the amplitude. That's why you already have lambda square here, but now I'm going to lambda square in the amplitude, in m, right? And diagrams, I won't draw them all because there's kind of a proliferation of diagrams now, but I can put it like this. Let me write one good example, which is this one. But again, A, B, 1, 2, right? These are index for the momenta going in at those points. And I have one extra interaction here. So there's an interaction here, another here. That's why order lambda square. You can convince yourself easily. Just draw all the diagrams, but that the only connected diagrams look like this, right? They have, let me qualify that. There's 4 diagrams that look like this. I can put this here, here, and here, and the discussion we're having is valid for all these options. And you also have diagrams that look like this, right? Which I'll treat later. But let me talk about this one first. And then a bunch of disconnected bubbles, those I won't worry about. Right? So let me use the fine rules I know. There's a symmetry factor of 2 there. I have a minus I lambda for this guy, right? Total momentum conservation for the external momenta, PA plus PB minus P1 minus P2. Now minus I lambda for these other vectors. And an integral in momenta for the loop there. That's the integral of d for k. Actually, let me organize. Let me write first 2 pi for propagator of k, right? And then there is this propagator, right? df of, I can call this, let me write the momenta here. So I'm calling this PA, right? That's the easy one, PA, P1, P2. Those are the obvious ones. But in here I call the momenta that is going around the loop K. That's why I have this integral over K and propagator for K. I have PB going here, right? And I have this, what I call P prime. But by momentum conservation, P prime is PB, right? So I'm writing just the propagator of PB here. Right? What I want you to notice is that this guy, let me bring this minus I lambda here, this guy right here is actually part of something else, right? This guy can go out of the integral because it does not depend on k, right? The momentum conservation does not imply any relation between this p prime and k, right? And this piece right here is actually a part of the 1pi function for the propagator of the scalar theory. If I write the full propagator for this theory, I'll get something like this, right? This is the full propagator. The first piece is always the free theory propagator, which is not included in the 1pi function. Remember, I'm talking about that thing that I called pi2 back when we were discussing 1pi functions. But the first contribution to this guy, right, which does not include that, is exactly what is in purple here, in pink, I don't know, right? Is exactly this piece. And it is customary for scalars to call, well, we call this pi2 function by a different name depending on the particle, and it is customary for the scalar to call this minus I, this is just a convention, m2. M2 means the same as pi2, so it's a 2.1 pi function, right? And this is at first order perturbation theory, so let's keep a number right here, right? So the 1 pi function is starting to appear here in these diagrams, right? And of course, there is a little bit of a problem here, right, that we have already discussed a few times, in that if I write this expression, let me just copy everything here. This part is fine. Then I have this function minus I m2 1, right? And then I have this propagator, but this propagator now is kind of problematic because there's no integration in this momenta, PB, right? And PB is the momenta of an external particle, and that is a particle that is on shell. So that propagator is blowing up. And it doesn't even help to remember that there should be a plus I epsilon here, because eventually I have to take epsilon to 0 at the end of the calculation. And since these two guys are the same, this will be exactly 0, and I just postponing the problem, right? This is blowing up when I take epsilon to 0. Right? This is a problem that I hope you can see will show up every time one of these 4 external momenta here, and more in general for bigger point functions, every time an external momenta shows up again inside the diagram. Because these 4 momenta that are here at the external legs, they are fine, right? We have seen that if they through the calculation, right, they will go into those exponentials and become this total momentum conservation. They will not end up in propagators. But when PB shows up again inside the diagram after some vertex, then there is a problem, right? So let me state that problem in general, right? In this way, imagine a very complicated diagram. Again, we're thinking about lambda phi 4, and just for the sake of illustration, I'll draw a very complicated one. Unnecessarily complicated, but I want to convince you, right? And I need to improve my drawing skills, right? So this is external legs, this is the complicated diagram, and this goes into another complicated part. Again, this could be anything that then goes to external leg, right? So if I use a color code here, these are the external momenta that will end up in my, let me not call them by the same name, it's on the same momenta, right? These guys in blue are momenta that are external. Let me call this just external momenta. And those I don't have to worry about. I know what happens to them. They will end up here, right? These are off-shell momenta, all of these in green. That are internal to the diagram, and they are combinations of these guys, in a way that any of these momenta square is not even the mass, right? These p squares are not m square, and also they are integrated over, right? All these momenta here, I don't have to worry because they are off shell anyway, right? And they will appear in propagators and be integrated over, right? But there's one problematic guy that shows up here because I don't even need to know what happened here. Whatever momenta went in, by momentum conservation, must come out, right? And here I have a on shell momentum that is problematic. And that will happen every time I have all the momenta that went into a leg, do a lot of complicated stuff, and goes back into one propagator, right? This is the piece I have trouble with. Now, this shows us that I can quite generally write any diagram, right, in the following way, right? Let's suppose I just put in the middle here any 1pi diagram with n external legs, right? And then I put n external points, x1, x2, I don't know how many others, right? xn minus 1, xn, right? And I want to connect those external points to that 1pi. The most general way I can do that is go through a full propagator, back into one line, and then go into that one. This guy is the complete propagator, which I don't need that C to indicate. It's just the sum of all connected two-point functions, right? I can do the same here. I can do the same here. And here. And you have other legs, right? In which all of them I can do the same separation, right? So essentially my statement here is that I can write any diagram in the theory like that. I'm just separated the 1pi part that cannot be separated in just on-shell momenta and 2-point 1pi functions from the 2-point 1pi functions, which I'm keeping here in these now more complicated external legs, right? If I draw the momenta in the same color code I did before, I have P1, P2, etc., all the way to Pn minus 1, Pn, right? And I have problematic guys here. And I know there's no problem inside because all the lines inside are not equal to the same external momenta. They are integrated over. They're running over a variety of values for momenta, so they're not on shell, right? And now what I want to do is get rid of the red propagators, right? The red momenta. And that's what I call imputating a diagram. Right? So let's define the operation. Right? Say I have a diagram like that. Again, I'm overly complicated on purpose. And this goes into some one pi function with a lot of legs, right? What imputating, and let me color code the momenta, right? And these are the problematic ones. Right now I have problems in two places. Right? So I have that blowing up propagator square in this case. Right? What I call imputate is actually going through a line as far as I can from the external point, right? And cutting at the last propagator that actually shows P1 again, right? Which in this case would be right here, right? And this is what I call an imputated diagram. It's just this piece, right? Without this propagator. This is now an external leg and has momenta P1 going in. So essentially what I get is the 1pi endpoint function. And I remove all the 1pi 2-point functions that are going in. Now let's see what the LSZ does, right? Because what I said before is that the LSZ formula only includes these imputated guys, right? That's what I'm saying up here, right? And I want to show you exactly that, right? So let's write the LSZ, not in that practical form I wrote above, but in its full glory, right? This is it, out. Set of outgoing momenta, right? N. The ingoing momenta I call K, M, in, right? This is the limit of pi squared going on shell. This includes the possibility of each particle having a different mass, but in our case they all have the same, right? Kj squared goes on shell 2, right? And this is the formula, 1 over I square root of z m plus n, product of I going to 1 all the way to n of pi squared minus mi squared plus I epsilon, mj, another product from j going to 1 all the way to m. Same thing for the k. And here I have the n plus m green function in momentum space. So this is a function of all those momenta, right? I won't write here because I don't have the space. Now, this is the main point, right? The problematic propagators are here, right? All the green, all the red propagators here are in there. But look outside here, right? The main point, the main assumption you have to make here is that the full propagator, right? We know that the perturbative propagator is just this, right? The free theory propagator, right? Let's call this M0 as the mass in the Lagrangian, right? But now we know there is an object called the full propagator. And we actually have shown that this is a sum of 1pi diagrams, right? This is a series we have looked into a few videos ago. It looks something like that, which I can resum, and we have seen the expression for the full thing. The main point here is that since I'm taking this limit, right, I don't have to know the behavior of the full propagator everywhere. I just have to know this behavior close to these poles, right? And close to the poles, all that matters is the position of the pole, right? I need to know where the pole is. And I need to know its residue, right? So this guy behaves near these poles where this limit is being taken as I z p squared minus m squared plus I epsilon, right? So I'm parameterizing the position of the pole by this m here, which is not the mass of the Lagrangian anymore, is the position of the pole. Whatever that is, we have to calculate it to find it, right? And this is the residue. It's controlled by z, right? If that is true, right, then I can rewrite this expression. Let me copy it. Right? Or better yet, all that matters is this part. Right? This part of the Lagrangian, of the LSZ formalism, can be rewritten as Right? Let me take a factor here. Right? This is the power of I, z that I want to throw in. So I take square root of z here, m plus n, right? And throw inside this product, I forgot one product. So I'm taking out this power of z, right? And rewriting those products let me put the limit here and repeat the equation, right? If I take this out, what goes in? Then I get an extra factor inside each of these guys, right? Of, let me write like that. This becomes Iz, right? So I took, in this case, n powers of square root of z outside, right? That gives me a power n of z in here, and the I just brought here. And I'll do the same for m, right? So this product, let me erase this, right? This product also becomes this, right? Which is the inverse of this expression. So if the full propagators are behaving like that near the pole, which is where I'm looking, right? And I'm multiplying by that, right? All the full propagators are eliminated. In fact, this, by the same logic, this is how that function gamma 2, which I have shown is the inverse propagator, behaves near that pole. Right? That's the expression for gamma 2 near the pole. So really, what the Lsc formalism, reduction formula actually, is doing is removing not just this guy, it's removing the whole sum, it's removing the whole thing. In other words, it is imputating, right? It's removing. When I apply Lz, I'm cutting this thing right here, right? Removing the full propagator from the external legs. And then the problem is gone, right? I have finally this useful relation, which is, again, another version of that practical Lsc reduction formula I started with. I'm just writing this left-hand side now in terms of the matrix element, PA, PB, minus the sum over final momenta, right, is equal to a sum of connected and imputated diagrams times, and this is the important part, square root of z n plus 2, right? Here, because I'm putting 2 incoming particles and n outgoing particles, right? This is the same as m plus n there, right? And this is important because on one side, it shows us that these full propagators will be amputated, but it also tells us that they will have an effect on the cross-section, right? Because this z right here is the correction of the residue of the propagators, right? And it stayed behind, you see, some power of z stayed behind. And that means that the changes in the propagator won't be just completely invisible, right? They will change the total cross-section, right? That is one of the factors that will lead to the running of the coupling constants. So we'll see that these theories suffer significant changes when you go to loop corrections, and that's one of the loop corrections. And that's why z is 1 at 3 level calculations too, right? This problem never shows up unless you put loops, right? It should be clear that then you just have to imputate the free theory propagator. Right, so keep that square root of z in mind, because it will show up and it will multiply whatever was m before, right? And now we get finally to QED time, right? So as the name says, quantum electrodynamics is the quantum field theory version of electrodynamics, right? We want now a quantum field description of electromagnetic interactions, right? In order to do that, I'll need the electromagnetic field, right? And some charged particles, which will scatter against each other by electromagnetic interactions, right? For simplicity, I'll start with one charged fermion and one charged scalar, right? I could put more fermions and more scalars, but unless I put some other complication between them, some interaction or some other symmetries between them, they'll be just copies of whatever I get here, right? With these three components, right? Of course, the last one is the electromagnetic field, right? The Lagrangian I'll write is this one. First at Minkowski space, right? So I'll call this the Lagrangian of quantum electrodynamics, right? In Minkowski, right? And this depends on the electromagnetic field, one scalar, one fermion, right? And remember, in order to have charge, this scalar needs to be a complex scalar. So this is the piece we have already looked into, right? So this is what we have called in the past the Lagrangian, electromagnetic Lagrangian of A, right? Then I have a piece that is this one, which looks a lot with what gave us the Dirac equation, but now with this derivative. And this Lagrangian now depends on the field and psi, because the covariant derivative here, right, let me define it, is del slash is just gamma mu d mu, and d mu is del mu minus I e, the charge of the electron, right? A mu, right? So now there is also, besides the kinetic term for these fermions of mass m, right? There's also interaction psi bar A psi, and we'll take a look at that interaction. That's the new thing here, right? Is this interaction between fermions and the electromagnetic fields. The scalar part is this. Again, I'm exchanging the derivatives by covariant derivatives now, del mu psi, and I could have some potential for the scalars, which could be a lambda phi 4. Also the mass term for the scalars, if I have a m phi, it will be here, right? Phi star phi, and I could have a lambda 4, phi star phi square, whatever. I won't go too much into details here, because that's a dynamic of the scalar sector that don't really matter for the electromagnetic theory that I want to describe. Right, so this is the Lagrangian that depends on the field and on the scalar, the complex scalar, right? And of course, F mu nu, I have defined it before, everybody knows it, is del mu A nu minus del nu A mu, right? And and that's pretty much it. It's easy, right? It's just algebra to check that this Lagrangian has a symmetry, which is this one. If I transform the matter fields, we call the psi, the fermion, and the scalar the matter fields, because they will be the charged particles that are moving around in this field, right? If I transform them both in this way, psi x exponential of I, the electric charge, and some function of position, this is arbitrary, right? I do the same with the complex scalar field, phi x exponential of IE psi of x, and I take the gauge field and transform in this way. Then this Lagrangian is invariant, right? If I do this transformation on the fields, these will leave the Lagrangian invariant, and these transformations form a group, is the U1 group in its local version. So this is a gauge theory, right? I'm using local parameters for the transformation, right? So I advise you to do this calculation and show that this Lagrangian is invariant, right? Now, before quantizing, I want to do what I have been doing so far. I want to go to the Euclidean space, right? And that means exchanging, right? I S in Minkowski by minus S Euclidean, right? We already did this for most of these theories, right? We did this for this part, most of these, right? I'll just list the conclusions here. So if you look at, let me use a color for the pages. If you look in my lecture notes at page 106, you see that the Lagrangian in the Euclidean for the scalar is just del mu phi star del mu phi plus v phi star phi, right? All signs are already taken into consideration, so this is really the Lagrangian that goes in here. All factors of I have already been taken care of, right? And I don't care about lowering or raising indexes anymore because this is Euclidean, right? If you look at page 140, then you have this for the fermions, right? For the kinetic part, actually, right? Mu del mu plus m psi, and in there you can see how the gamma, the Dirac matrices changed when I went to Euclidean, right? Now they satisfy the Clifford algebra for an Euclidean space, right? I show the same for the electromagnetic part at page 167, and the result was this plus 1/4 f mu Euclidean, right? All these functions are now the Euclidean versions, right? I'm not repeating these Euclidean everywhere, right? The only new thing that I didn't do before is these terms that are linear on A, right? That appear in here and in here, right? Then you have some linear terms on A, on the electromagnetic field, and that I need to spend a few seconds thinking about. So the electromagnetic field in Minkowski is given by A0 and AI, right? And I have shown close to this page that this guy rotates in this way, right? Consistently with its dimensions, right? But and now I need to see how it behaves inside these places where it shows up. It turns out that since it has this mu index, right? A mu is always contracted with either another A mu, a del mu, or a gamma mu, right? And these guys, right, the A0, the del 0, the gamma 0 transform in this way. So A0 goes into A4, del 0 does the same, right? Gamma 0 now has no I, right? And gamma I, which is the other parts of gamma, because the I part of the derivative and of A does not transform at all, right? But gamma I does, goes into I, gamma I Euclidean. But again, I'm suppressing this Euclidean, right? That means now a bunch of things, right? That means that del mu phi will go into minus del mu phi, right? These are already used in there, right? But A mu phi, del mu phi, do the same. And that is also true for A mu phi. This goes into A mu phi, right? And that means that this whole part here with the covariant derivatives will, all the pieces that are here, right? The derivative field or field, they all change with the same sign. Right? All these parts change with the same sign. So I can just go here and change this to the covariant derivatives. Right? In the case of the fermions, right, psi bar I del slash psi changes into psi bar del slash psi. Now everything is Euclidean, right? And psi bar I a slash psi will also, just look at this part and this one, right? Will also just change in the same way, but Euclidean now. Again, that's good because both parts in this kinetic term right here, both the part that involves the derivative and the part that involves the field change with the same sign, right? Which means, again, I can just put the covariant derivative here. And that means life is easy, in this case, that the Euclidean Lagrangian, and this is the last time I'll write Euclidean, of these three fields will be 1/4 f mu squared plus psi bar del slash plus m psi plus del mu phi star del mu phi v of phi star phi. And that's the theory I want to quantize. The thing is, we already did most of the quantization involved here, right? We did individually. We quantized fermions, scalars, and the gauge field, right? So my job now is mostly to convince you that those individual quantizations still hold, right? and then attack this new interaction, right? These terms that are hidden here in the covariant derivatives, right? The most complicated quantization was, of course, the gauge field, right? So we have shown that in order to quantize the gauge field, I needed to do some trick, which in the end, the Faddeev-Popov trick, amounted to gauge fixing the theory, right? In the way that I got an effective Lagrangian, right? That was this original one, written here in this case, plus a gauge fixing term, right? And this turned out to be and I have a choice here of alpha that will give me different gauges, right? And in doing that, I needed to prove some identities and do a change of variables in the integral, right? And you could wonder if this new piece here would change any of that, right? The main argument you have to remember to see why it doesn't change is that the only thing I used of my full action was that this action was invariant under a gauge transformation, right? I used that when I decided to separate the integral over these gauge parameters from the integral over A, which was an A of psi. And once I got rid of this, I got just a multiplicative factor. But in order to do that, the exponential here should have an action which was gauge invariant, which is still true, right? So this Lagrangian is gauge invariant as a whole, right? This piece is gauge invariant by itself, and most of the other pieces, this piece is gauge invariant by itself, this one too, right? Written in this form, each piece is gauge invariant. So I'm fine. I can do the same trick, and I'll get to the same result, right? But instead of having just this L of A, I have this whole thing, and I still get a gauge fixing term that will combine with this one, right? I can write now a quadratic term for this and get the photon propagator, just like before. So that's the first thing I do, right? I use the Faddeev-Popov trick and fix the gauge in the Lagrangian, and I don't have to worry about that anymore, right? The next thing would be to find the propagators, right? And the way to go about it is first to notice that there are some interactions in this Lagrangian. Let me write explicitly, for instance, the one that comes from this part. It will be something like gamma mu, actually psi bar, gamma mu, a mu psi, right? That's what comes out of here. From this part, I have more than one interaction. One of them is just psi star, psi, a mu, right? So you have interactions like this in there, right? The way to approach these interactions is the same as we have been doing before, right? I take this Lagrangian, right? And I add to the Lagrangian a bunch of sources that in the end I can take to zero if I'm dealing with a situation where there are no physical sources, right? So I can put a source for the gauge field, for the electromagnetic field, sources for the fermions. Remember, I need two of them because this is a complex field. Same for the scalar, right? Again, now that I'm dealing with the complex scalar, I need to put two sources. Right? And then I can rewrite the exponential of the interacting part of the action, right? I can separate all the interactions in a separated piece of the Lagrangian and rewrite the fields in those interaction terms as derivatives acting on the sources, right? That will allow me essentially to rewrite my full partition function for the theory, which is a function of all these sources, as the exponential of the interacting action, but in here instead of having the fields, I have derivatives on the sources, all these sources, right, acting on path integrals that are now completely independent, right? Once I separate the interactions, the exponential for this part plus gauge fixing only involves A. This part only will involve psi because I took the interaction out, and this part will only involve the scalar. In fact, I am only leaving the kinetic part of the scalar here. This also goes into the interaction part, right? With the exception of the mass. Could be a mass here, right? On this part could be a mass. The mass I keep here, but I send all the interactions into this interaction action, right? And then my full partition function will look like SA, right? This is the effective one, so gauge fixing goes here, right? Times del psi bar, exponential of minus s of psi, times del phi star, exponential minus s of phi, right? And the reason I can separate these integrals like that is because these actions only depend on one of the fields, right? In this case, psi bar, in this case, phi star, but you get the idea. The interactions are all separated. And then it becomes quite clear that I have basically three separated theories that will only mix once I take the interactions into account. But I separated them out here. These will be, I can do this integral, right? This will be just exponential of j mu delta mu nu j nu, where this is the photon propagator. This integral I know how to do too. It will be just psi bar fermion propagator psi, right? There's the scalar products hidden here, right? Here too, right? So they are integrals on the variables. And this guy is the famous j delta j, just for a complex scalar now. So there's a j bar there, right? So I hope that makes very clear that I don't have to quantize all these theories again. At least the propagators are the same, right? And now I just have to act with these interactions there and see how the vertexes look, because there's nothing to the propagator, right? With that in mind, let's forget, I'll give the, in fact, I think I already given the scalar as an exercise. Let's focus on the fermion for now, just to simplify things a bit. I hope I have convinced that these sectors are fairly separated between themselves, and the fermion is more interesting to us because we live in a world where we have electrons, right? So most of our electric phenomena is related to fermions interacting electrically. Although there are scalars out there too, but we see these the most, so let's focus on the fermion, right? What I'm saying is that if we focus on the fermion, we now can write a generating functional, which will be a function of three sources, psi and psi bar, and this is the path integral A, phi, psi bar, exponential of the effective action that now depends on A, psi bar, j mu, psi, and psi bar. Right? So let's deal with this theory now, right? And just to be thorough, let's write how an observable looks like, right? Any operator in this theory, right? The expectation value will be given by this thing divided by this thing, of course. with the operator here, now as a classical function, right? Divided by the same thing without the operator, right? Which gets rid of all the normalizations, vacuum bubbles. Now you probably get used to that, right? Now I'm interested in the 1-pi diagrams, right? The connected in the 1-pi diagrams. So I want to write, use those objects I have defined in the videos we discussed these, right? So I want to define Z, actually define W, which is given by this, right? So W is minus the log of Z. And then from W, get the generator of 1-pi diagrams, which is given by a Legendre transform, right? So now I define a classical, a psi bar classical, a psi classical. Remember, these are the vacuum expectation values of those fields, right? And these will be given in terms of W, J, psi bar, plus D for X. Right? These are all functions of X. J mu, A mu classical, plus psi bar, psi classical, plus psi classical, psi. Right? These are all functions of X. I could even suppress this and just put scalar products here. Looks nicer. You see, all those discussions really generalize because these variables are independent of that one. So the transformations are similar, right? It's very easy to get the proper relations, right? In fact, let me just write them here for reference. And you see how analogous this is to what we got for the scalar. When we did this, we did only for the scalar field. Now you can see how it looks for fermions and for the gauge field, right? The fermions take a little bit of more care, right? You see some signs here that come from the fact that they are Grassmann variables, right? So these derivatives are always acting from the left. You have to be careful how you define all those variables to take care of those signs that are coming from the fact that there are anti-commuting objects, right? Both psi and the source to the psi. Now, regarding the vertex, the interaction for fermions, right, is pretty simple, right? It looks like this. I just have to expand that part of the covariant derivative and get psi bar gamma mu A mu psi. There are a few indexes here that I have to be careful with, right? So there are spinor indexes, right? So this goes from 1 to 4. I have I, J here, and I have J here, right? So it pays to pay attention to that. Now we know, if you don't remember, you can go back to the, say, page 122 of the lecture notes. I do that for scalars, but this is the same thing, right? The rule for the vertex, right, which in this case will involve an incoming fermion, an outgoing fermion, because I have psi and psi bar, and one photon, because I have an A that creates or annihilates a photon. Let me do a proper photon, right? The symbol for photon is like an oscillation like that, is given by minus the derivatives in all the fields here, right? In this case, I have 3 different fields, and I have to do the derivative in all of them. These minus signs combined with that one to give me a plus IE, and the fields go away. I just stay with this gamma mu ij. And this is the Feynman rule in Euclidean space, right? This is the rule in Euclidean space. We'll rotate to Minkowski soon enough, right? What I want you to notice here, that differently from the Yukawa interaction that look a lot like this one, right? Just exchange these for a field, a phi field, right? In this case, the vertex itself is a matrix in spinor space, right? There's a gamma matrix there, a Dirac matrix, right? That means that before in the Yukawa interaction, you had just one index in spinor space associated with the vertex, which means that the field going in and the field going out all had the same index, right? This is psi bar I, psi I, right? And that would become a U I V I, right? With the same index contracted here. In this case, that's not true, right? I have two indexes associated here. One of the fields will contract with that, and the other one will contract with I, and the other one will contract with J, right? So now the fermion fields also rotate in this spinor space by the action of this gamma matrix, right? And this is new. I have to, again, be careful with these indexes when I'm contracting those traces of fermions, right? These gamma matrices will end up somewhere if I'm really careful with the indexes, right? Now let's write all the Feynman rules in Minkowski space, and here they are, right? So first I wrote the Feynman rules. Remember, we are now in Minkowski space, momentum space, which is the most useful one, right? So I have here the propagator for fermions, the same thing as always. Remember, carries two spinor indexes, so I'm using alpha, beta, and gamma here for spinor indexes. And those are the rules for external fermion legs that depend on if it's a particle going, an antiparticle going, or the same two options going out, right? And the spin state of these particles is encoded in this index, right? So fine. And also remember that if your diagram has loops of fermions, you have to remember of this -1. For bosons, there's a similar thing, right? We have already also quantized a gauge theory, right? And show that this is the photon propagator. Of course, it depends on the gauge you choose. Normally, you choose these according to convenience, which is almost always choosing alpha equal to 1, because you see this becomes a lot simpler, especially if you have to integrate over momenta later. It's much easier to integrate over this than this guy, right? And these are the rules for external photons, right? Coming in or going out. And same as the fermions, these encodes the polarization, right? And of course, then there's the vertex, right? Which has 3 indexes, right? You see that the role played before by the Yukawa coupling or the lambda coupling now is played by the charge, right? This is the fundamental coupling here, right? And we have 3 indexes. So I'm using mu, like I use here, mu and nu, to indicate Lorentz indexes that go from 0 to 3, right? And alpha and beta to indicate spinor indexes that go from 1 to 4 on a different space, right? So keep in mind that this index will be the same as the photon going into this vertex, either as an external photon, so mu would be the same as this one, so contracted, right? Or as a propagator, right? These guys contract with one vertex on the left and another one on the right, right? So there'll be a gamma mu multiplying this guy here and a gamma nu multiplying this guy here, because, and the same goes for the fermions, right? This index alpha contracts with the fermion going in and beta with the fermion going out, either through the index they have in this external leg rule, or in these indexes that are in the internal leg, right? So that will set how the Dirac matrices are multiplied to each other, and eventually there will be traces that you have to calculate. We'll get to that next video, right? And how do we use those rules, right? And now I just remind you of, like, wrap up what we know in terms of Feynman rules, right? So first you draw connected and imputated diagrams. Don't look, I mean, the whole discussion we did up to this point in the course, in the course, is actually to convince you not to be drawing vacuum bubbles and disconnected diagrams, right? The ones that matter are the connected imputated diagrams. So no corrections on the external legs, focus on the important diagrams, right? Then use momentum conservation to eliminate any internal momenta that can be written in terms of external momenta or in terms of each other, right? Whenever possible, reduce the number, use momentum conservation on each vertex to reduce the number of momentum variables that you have in your diagrams, right? Then use those rules, right? Use the rules above, right, to turn these Feynman diagrams into analytical expressions, right? And pay attention to the difference, the possible relative signs between diagrams, especially if you have external fermions, right? You have to think a little bit how the contractions have changed from one diagram to the other to decide on the relative importance, right? The relative signs. Right? Then integrate over any internal momenta that you didn't manage to eliminate in step 2, right? Of course, you're not integrating over the external momenta, right? Divide each of the analytical terms, right? Up to now, each of your terms in this big analytical expression is equivalent to a Feynman diagram. So divide them by the symmetry factors of the corresponding diagram, right? And multiply diagrams that contain fermion loops by -1 for each fermion loop that shows up there, right? That you get to a big analytic expression, and then you can use this expression here to get the matrix element, which is essentially just take step 6 and divide by I, unless you have loops, right? If you have loops, things get more complicated, because if you do have loops, then you have to calculate these objects, right? If you're going into one loop order, then you have to calculate it, right? I named the Z for fermion Z2, I named the Z for the photon as a Z3, and of course, to calculate this, you have to go and calculate the 1pi contributions to the 2-point function, which you have to use these rules all over again to calculate these things, right? This is the main preoccupation of quantum field theory 2, right? Second course will deal with how we calculate these guys and how they change the result. But if you are at 3-level diagrams, if you're thinking about 3-level diagrams, you can set these two guys to 1, right? And then you just divide step 6 by I, and you get this guy, and you can go have fun with calculating cross-section, right? So this is almost all of QED. There's one little detail left that you have to worry about, right? So now, if we want to calculate cross-sections using this, you have to square it, right? And when you square it, you have to decide on polarization. We already discussed what happens to the spin of fermions, right? If you averaging over spins, are you observing spins in the initial state or not? So you have to average over that, right? Before you calculate the cross-section. You have to do the same for photons, and you would think the whole discussion is the same. I just average over the polarizations of the photon, right? And this is almost true. The problem here is that since we keep our theory explicitly Lorentz invariant, that means there are unphysical polarizations in here. And we need to think a little bit about that. To make the issue more concrete, let me draw a generic QED diagram. So this is just anything, right? Any connected diagram, one PI function here, right? And for a generic QED event, I'll have photons and fermions going in and out of that diagram, right? Doesn't matter the number here. I'm just taking any generic thing. And I want to single out one photon because that will help me understand what happens with this spin, right? Say this photon has momentum k and it is going out of the momentum is going out of the diagram, right? Using the Feynman rules I have just shown, you know that these, after imputating and all of that, is equal to some matrix element, right? K. Whatever is on this side, this will be equal to I times the matrix element, right? And that matrix element depends on many variables, but it is also a function of K. Now let me divide this into pieces, right? We know that K is going in there, and wherever this photon is going, right, the photon itself has a polarization, and that polarization has a Lorentz index, which is contracted with the rest of the diagram. Specifically, it is contracted at the vertex where this photon is going, right? So I can, without any loss of generality, rewrite this in the following way. I just create another matrix element, let's call this M tilde, right, which has a Lorentz index mu, which is and again, this is a function of K, but also of other variables. And this is contracted with the polarization of that photon that is going out, right? I'm keeping generality here, so it's the complex conjugate of the polarization, right? I didn't lose any generality doing this because, you know, the polarization must be contracted, and I'm putting everything else in here. Whatever else appears in that diagram, I'm putting inside, right? And now I have to think how I would go about the polarizations of this photon, right? If, let's suppose, for simplicity first, I'm not looking at the polarization of this photon. I'm measuring photons, right? So I have to, again, same discussion we have with the fermions. If I'm not measuring the state of an outgoing particle, right, I have to sum over all possibilities. So I would have to sum over polarization over this matrix element square, right? And that's what goes inside the cross-section formula, right? Is this sum, right? This thing I can express now using this separation I did here in this way. I will suppress, but remember this guy, these other variables, but this guy can be a function of many things, right? It only matters to me that it is a function of K for the discussion we have in here, right? And that I can write, of course, as a sum over epsilon mu star epsilon u m tilde K mu and m mu star K, right? So that's what I get. Now I could simplify my life in terms of doing the most obvious thing and only sum over the physical polarization, right? I'm not obliged to sum over the non-physical ones. I can say, well, the photons I see, I only have these two polarizations, so that's the only two possibilities that I have to include in my cross-section, my probabilities, right? And that's easy enough to do, right? I just have to choose a direction, right? Let's put our reference frame in the direction of, in the z direction for that momenta, right? Then I know I can write k in this way, right? It's the module, the intensity of the momenta, right? And then the sum over epsilon becomes just the sum over epsilon equal 1 or 2. There's only two polarizations, where epsilon 1 mu will be this one, and epsilon 2 mu will be this one, right? The only two transverse polarizations to that momentum, right? And then, of course, that sum becomes real simple. And let's baptize these guys just m to the 1 k square plus m to the 2 k square. So m has a Lorentz index, right? Only components 1 and 2 survive. All you have to do is to put these vectors in and sum over them, right? And then you see that this is the expression, and really this is what physically matters, right? This is really what a physical process will produce. But it is an inconvenient form because I'm losing explicit Lorentz invariance, right? From that point on, when I go to my cross-section calculation, or in fact, I have to keep in mind this reference frame. I have to be careful when I put these in the cross sections. I will be integrating over a lot of other four momenta. I'm losing explicit Lorentz invariance, right, for my calculation. So it will be harder from this point on to change reference frames if I need to. It's a little bit inconvenient, but there's a better option, right, which consists in using an important relation that is a consequence of this being a theory, a gauge theory. A theory symmetric under local U1 transformations, which is the word identity, this one specifically. Right? I won't prove this relation here because of time constraints. Right? And there are two ways of doing it. One is diagrammatically, term by term in perturbation theory. That's what Peskin does in section 7.4, and I invite you to go through that as an exercise, right? And the second approach is to use an idea very similar to what we did to get the Schwinger-Dyson equation, or the general word identities, right? A few videos ago, and then get a general relation between green functions for this theory. Those are called the Ward-Takahashi identities in the case of gauge theories, right? And we'll do that in quantum field theory too. For now, I can show the consequences of this relation, and you see that they are reasonable, right? Take, for instance, this equation is specialized for this reference frame, right? Then this equation will become, with the momenta oriented like that, it will become k times the time component of this matrix element m tilde minus k of m tilde 3, right? And since this should be valid for any value of k, right, that means immediately that m tilde 0 of k must be equal to m tilde of 3, m tilde 3 of k, right? Which is important, right? Again, remember when we did the canonical quantization of photons, right? That similar ideas appeared, right? We could keep physical polarizations around, but always sooner or later there's some relation between these physical parts of my calculation, right? And that's what allows us to rewrite, right? We know that the physical answer is really this one, right? This is what really matters. But now, using this relation, I can just add another part. I can add, let me put this in a different color. M tilde 3k square plus, or rather minus, M tilde 0k square, right? Because this relation guarantees that this is 0. I'm just adding 0 here, right? But then I can rewrite this expression, right, like this. So I know that this part can be written epsilon nu star epsilon nu M tilde nu k M tilde nu star k, right? This is just what I had up here, right? I'm just writing this explicitly. This right here. And on the right side, now I can use this expression to write it as minus because the time part is with a negative sign and the space part is positive, right? And in our metric, we have the opposite situation. M tilde nu k M tilde nu star k. And this is a very useful relation, right? Because I manage to write the sum over the physical polarization in a explicitly Lorentz invariant way, right? Which means that this relation is true in any reference frame, not just the one I used, right? And I can rest assured that on the right side here, the unphysical part is canceling itself out because of the word identity, right? So I'm calculating really the physical thing. And now I can use this because this is for just one of the photons, right? But either if I'm summing over the polarizations or averaging over them, this is what will appear, right? I'll have the polarization of that photon. I have 2 here because I'm taking the matrix element square, right? But these are 2 polarizations for the same photon, right? So this is summed over. And then I have a relation very similar to what I had, right? In the case of the fermions, for instance, I had a relation, right, to do the spin sum, for instance, for a fermion, which was US of P, U bar S of P was the same as P slash plus M, right? It is not true, and you have to be careful with this because that causes a lot of confusion, right? That the sum over the polarizations is equal to minus G mu. But this equation right here is true, right? So you can safely substitute in any calculation that you're doing epsilon nu, the sum over polarizations by G mu, because in any, right, in any calculation where you have photons, right, this is true for this photon, but it's also true for all these other photons. These photons are going to a QED vertex, right? And in there they will be contracted with the rest of the diagram. So in any scattering that involves photons, it is safe to use this trick to do the sum over all polarizations of the photon and then substitute that sum, right, in the relation where these indexes are contracted with the rest of the diagram, right, by minus G mu. And that's a very useful way of dealing with photon polarization, right? So this is it for today. We basically have everything we need to start using QED, at least at 3 level, right? And over the next 2 videos, we'll be using that to get some classical results, classical in the sense of non-relativistic, so we can find the equivalent potentials that I would get from this theory if I was doing quantum mechanics, and also to do a proper scattering, right? Take some relativistic result out of here. Okay? See you then.